VOA. Is robotics operator?
Yes, so the title for today, or for a third lecture rather, is VOA often 4. So my goal is to give an explanation of what the title means. So that's, I hope in an hour we all know what it is, at least what it stands for. But before I proceed to this topic, I should make slight comments on what we discussed in the second lecture. Namely, these are correct descendants of integrands to vertices and edges of what we call plumbing graphs, or think of them just as graphs. And perhaps one correction, I mean, everything was pretty much correct the way it's written. And one thing I should not have emphasized as strongly is the relation between U and X. So think of, in this particular variant, so we had 3 variants of calculus, of integrals, and there are many more, so these are just examples. But in this variant, we integrate over this variable u, which runs over real x's. And just don't try to think about relation to x. In fact, that's what got me confused. So when I wrote this x equals 2 pi I u, so this indeed is how I obtained these expressions, and I can give you a quick comment how I obtained it, from where it came from, but just don't think about it. So then this is not relevant, and if I were to present it to you, I should have just done this. And the only thing I want to say about this integral, and there was indeed a question, do you have any suggestions how to evaluate it? The only suggestion I want to make is that to make the integrand nicely behave, let's multiply it by e to the I theta, or a theta, or let's call it this epsilon, to suggest that epsilon is very small. And then my only suggestion is compute it on Mathematica. I mean, it's really not a big deal. The answer is going to be a number for the homework I suggested. And it's actually fun to see that this number is indeed the same for all of these plumbing graphs related by moons that we discussed before. So plug in some small value of epsilon, compute to great accuracy, and you'll see that it agrees. Of course, the logic here, as usual, in calculus, we want to take epsilon to 0 in there. Now, I want to point out how I got to this and what led to this slight confusion with x's. So there is actually a generalization of the story, which as integrand involves quantum dilogarithms. And that has yet another parameter in the game, parameter which is usually called either h bar or b, or there are many other notations for this fellow. And I decided to give you a simplified version instead of discussing quantum dilogarithms, which many people love, and then actually that integral is better behaved in a sense. You don't have to worry about such regularizations because it avoids all the poles and is nicely convergent. In fact, in that case, it is defined in terms of variable x more naturally. But I decided to take the limit where b is equal to 1. And after massaging the integral, this is actually one of the limits where quantum dilog degenerates into trigonometric functions, or sines and sinches. And that's why I decided to give this version. It's just simpler, but it hunted me in the end. And anyway, that's the one correction I want to make. Another comment I want to make quickly about the other version of the integral, which again was well behaved with respect to these moves, is the power series, which turned out to have integer powers, integer coefficients. And even though I pose this as a question, what are they counting? I want to give an answer which is correct, but and conceptually how it came about, and that connects to the first lecture, that these are counting open BPS states. So if you use this framework that I outlined in the first lecture, that counting should give you integers, and these are precisely those coefficients of the Q series. The only thing is that the way it's set up, for example, using topological vertex techniques or this refined topological vertex techniques and things like that, it's very limited as far as computational power. So if I were to use to check this equality, there are very few cases where I can really check it term by term. And as we could see here, we can compute it more or less for any 3-manifold. And it would be nice to develop this part of the story to the same level of technology where we can really see the relation. But I just want to make a comment that in some sense, there is reason for integrality, but I want to still pose it as a question. It would be nice to explore it.
Does the mathematical meaning of the right hand side sense only if to have a torus section?
Yes, as far as I know. Yeah, I think again there are many more experts in the audience on attempts to define this mathematically from various perspectives. For non-toric Calabi-Yaos and setups, but again, I don't know when this Lagrangian brains don't preserve the torus action in a toric manifold. There might be some technique, but I'm not an expert on this. Okay. So.
No, there is a.
Huh?
I didn't understand the comment. There is a mathematical definition of that.
No.
Yes.
No, there is a Gromov-Witten invariance.
No, there is a PPS.
Oh, PPS.
What is it?
Davison and Swain-Hart.
No, no.
Yes.
No, not at all.
Well, I think it would be okay to say that this is definitely developing area. So I think this would bring all of us on the same footing. And in fact, that's why I guess I'm emphasizing it, because for younger generation, this is something that you can develop better and satisfy myself, Jan, and others who would like to have better understanding.
So what is kind of thing? Is it just potential boundary MC?
Yeah, so the setup was that for given M3, you would take Calabi-Yau, local Calabi-Yau, and you can take more general ones, but it's okay to take T star of M3 and work with a pair, M3 and T star of M3. So basically, this is what this open BPS series is supposed to be exploring. So one thing one can do, and this is how it has been done in some cases, one can study Gromov-Witten invariance of this pair, which is slightly better defined. Even that requires quite some work, but even that can be done. And what you obtain as a result is a series attached to this data, namely a free manifold, which is power series expansion and variable h bar. I'll call it h bar. And then you notice, well, coefficients of this expansion, this is also a power series, just like what we saw, but coefficients of this expansion are not necessarily integers, so this leaves in Q. In fact, it's a formal power series in H bar.
And that is about after genus.
Huh?
That's about higher genus.
Yes, exactly. Yes. This is higher genus version. But then, at least in those simple examples where people managed to compute it back in late 90s, I guess, they notice that if you write it in terms of Q, which is exponential of H bar, it turns into power series in Q. This is like huge infinite upper triangular transform from H bar series to Q series. And they notice that coefficients become integer. And that became known as integrality conjectures and all kinds of things. So this is morally what this BPS open is supposed to be. But again, I say morally because I would love to have, I mean, you saw my thematic, it's just 2 pages, and I would like to have the same thing for this BPS open. You just push a button for a given data, and it spits out a Q series. So again, it's available in this form, but I would love to have at least more user-friendly definition, even if Tony says that there is one. Okay. Good. So now my job is to proceed here, and I want to point out that something we discussed before, namely this graphs with labels. Things like that. So, and we have decoration A1, 2, A3, and so on. They not only define 3 manifolds, but they actually define 4 manifolds with boundary. So given every such graph, you can associate a 4 manifold. I'm going to call it M4. And in our previous discussion, 3 manifold M3 was actually a boundary of this M4. Okay? But the reason what we considered previously is part of the Kirby calculus is that there is a construction of 4 manifolds given such a graph. And in this case, for graphs that we discussed so far, what you get are simply connected four manifolds. They are non-compact. So they have this boundary on 3. And we saw a lattice appearing in our game. So it was basically z to the total dimension of this graph. And you should think of this, and this is not a lie, as really a second homology or cohomology lattice of a four manifold. So we also introduced matrix Q, which was a symmetric form on this lattice. And this Q is basically intersection form. On H2 of M4. And obviously, so the way this construction goes, I'm not planning to explain it in detail. That would take more than one lecture. In fact, you could have a whole course on Kirby calculus. But basically, the idea of Kirby calculus is that you start with a four-dimensional disk, or R4, and start attaching to it other disks in such a way that you treat their boundary in a careful way. So it's how they're attached that constructs topology and, in fact, smooth structure. So here I should say that it's not just a four manifold, but rather smooth four manifold. That will be important for us. And each time you attach a new piece, like a new ingredient in building the topological or smooth manifold, you add a vertex to this planning graph. How you attach it is encoded in connectivity of this graph. But basically, each time you add a vertex, you create an extra generator in H2 homology of your four manifold. It still remains non-compact, so it still has a boundary as a result. But yeah, now it has a lot of homology or cohomology inside. So simple examples, just instead of going through general theory, which again will take way more time and astray from what I want to say, I just want to connect it to our previous discussion and give you a couple of simple examples. So suppose your graph consists of just a point with label minus p. Okay? So from what I just said, you should expect that the corresponding four manifold in this case has 1-2 cycle. So it's again going to be simply connected. It's non-compact. And these labels that sit on top of vertices now encode the normal bundle to the 2 cycles. So what this really is, in algebraic geometry language, this is total space of O minus P bundle over CP1. Okay, that's what this is. And indeed, remember previously I said, so this is equal to this, that when we really cared about three manifolds, I said that this corresponds to M3, which is a length space, and indeed, the boundary of this total vibration of Euler number minus P over 2 sphere is indeed the length space LP1. Good. So I should also point out that there are now what we discussed before was operations on this data of how we glue basic pieces in such a way that three manifold boundary doesn't change. So that was equivalences called Kirby moves. Now, if you look at this diagram and you're interested not only in the boundary, but also in the four manifold that it really constructs, so it comes for free if you wish, then four manifold will actually change if I start doing some of the operations I mentioned earlier. Indeed, from this fact, it basically follows that B2 of your four manifold is essentially number of vertices in gamma in this graph, And if I start changing number of vertices, of course, my form manifold cannot no longer be the same. I don't need any fancy smooth invariants to detect it. I just see it from this simple fact. So for this reason, there are two types of Kirby calculus we should distinguish, and I want to distinguish them carefully. What we discussed so far is a so-called 3D version, Kirby calculus. In fact, it's kind of ironic. We got Kirby calculus out of the usual calculus, right? And then there is a 4D version of Kirby calculus. Which at the level of 4 manifold M4 and its boundary M3 behave as follows. The three-dimensional version of Kirby calculus did not change M3, so that was part of the game we played, but it does affect M4, so it does not preserve M4. And four-dimensional version, which I'm not going to explain in detail, maybe except for one exception in the end of the talk if I have time, preserves both of them. So this is slightly more delicate and in fact more fun type of operation. But this is just to put our discussion in perspective and connect it a little bit with Poynting graphs that we already had to learn in the previous hour. So, in this last hour, I want to do the following. I want to, in some sense, address the question, where is it all going, or what could it be useful for? So, as a result, I'll bring us a little bit closer to cutting edge of research, and this, in fact, is now based on joint work in progress with Boris Feigin. And I put ... here in case if any of you want to join this project. It's a massive endeavor, and as you'll see, it's fun, but it's delicate, so therefore we welcome any helpers. And it heavily builds on past work, which is already available online, with Abhijit Gade, Pavel Putrov, and also another work with Mikhail Dedyshenko, and Pavel Putrov. In fact, the second one is where this term VOA of M4 was officially introduced, even though not explicitly, it was essentially discussed here as well. And all of these are young people, so if you want to hire them, I can vouch for how great they are, and I'm glad I'm recorded.
And you vouch for Pavel twice.
Well, thank you. You're also recorded. Oh. Okay. So I'll give you motivation for why we're doing this with Boris and with this young gentleman. So mathematically, I'll give you two motivations, mathematically and physically, what the goal is. We want to study smooth structures on four manifolds, and this is tough. So this is not going to be easy, because this is long-going study and one of the most challenging problems in low-dimensional topology. So we shouldn't expect free lunch. But before we proceed, we should also understand what the standards are and what are the best tools on the market that allow us to study such manifolds. And best tools on the market are Donaldson-Witten. I'll abbreviate this as DW invariants, and Cyberquit invariance. So this usually is abbreviated as Cyberquit. And in fact, I already saw their baby version for 3 manifolds appearing in concrete calculations in the second lecture. So these are extremely good, extremely powerful. They help us to study symplectic structures on 4 manifolds, for example, whether they admit to or not, and so on. But these are not complete set of invariants to understand smooth structures, and you can either show this by rather explicit constructions. Even on 4-plane R4, you can have many exotic structures, smooth structures which are not related by diffeomorphisms. Or I can say one of the following results, which holds equally well in Donaldson-Witten as well as in Cyberquit theory. So this is a theorem, and of course it's attributed to different people depending whether you work with Donaldson invariants or Cyberquit invariants, that all of these guys vanish if you consider 4-manifold M4, say, let's take for a second compact ones, M4 and M4 prime. And if you compute this invariant, I'll call it Z, which could be either DW or SW, with rather mild assumptions on topology of M4 and M4 prime, these invariants automatically vanish. So just once you take the connected sum. Connected sum means you excavate a little ball from each one of them and then identify the 3-sphere boundary. So therefore, this invariance vanish for large class of 4 manifolds obtained by connected sum construction, which is one of the basic operations if you want to actually build manifolds from gluing basic pieces like we did in the second lecture for 3 manifolds. So therefore, we need something else that wouldn't vanish in this case, and in fact could potentially distinguish smooth.
I'm confused. I mean, aren't there exotic smooth structures on connected sums? What about this?
Only, perhaps only in the case where these mild topological assumptions are violated. So here, the basic assumption is that B2, assume for simplicity that they're simply connected, and B2 plus of each guy is greater than 1.
All right.
So
blow-ups are not.
Exactly. Perhaps you can even push this boundary of assumptions even further, but again, for illustrational purposes, this is correct theorem as stated. In fact, this appears in the first prominent paper of Simon in the Donaldson. So therefore, and the same is true for Cyberquit invariance. So partly for this reason and for many others, in topology, there was an ongoing search for new 4-manifold invariants. And when I talk to people like Tuchel, Stern, and other practitioners of these hardcore gauge theory invariants, they actually, surprisingly to me, encouraged to look for something quite exotic. So this happened way before I got interested in the subject, and I asked, what do you mean by exotic? And they say, well, may not even be formulated in terms of traditional gauge theory, because we really tried hard, study gauge theory invariants with different groups and ranks and so on, and they always boil down to various combinations of Donaldson-Witten and Cyberquit. So they encouraged trying really something out of the box. And back in the day, I had no idea what this meant. I still don't, but what I'll offer you is indeed quite an orthodox version of the invariant, which nevertheless is not too far from traditional gauge theory formulation. And if I'm continuing with mathematical motivation, one goal is to study something rather traditional, I would say. Given 4-manifold M4, and a choice of compact, simple gauge group G, I'll take this as a gauge group. So M4, G. You can study moduli spaces of self-dual connections These are so-called instanton moduli spaces, precisely as Donaldson did for SU2, and they're labeled by second Chern class of the gauge bundle. These are moduli spaces of n instantons on a 4 manifold. And you can try to ask, what about their cohomology, by which you may mean generalized cohomology, either cohomology or K-theory, or something else that you prefer. I'm going to refine some of the statements as we go and as we understand them better and better. But natural thing to do would be try to put all of these gadgets together, sum over n, so declare that this is some total space V. So what we're going to ask, is there some natural algebraic structure that acts on the space? So in short, this VOA of M4 that I'm trying to explore is vertex operator algebra that acts on this huge space. So this space is, in general, maybe infinite dimensional. The algebra is also infinite dimensional algebra. And the question is, can we understand, instead of individual cohomology groups, which may be hard, the algebraic structure? And as a result, this TQFT, because all of this is supposed to be preserve gluing, cutting and gluing operations on a 4 manifold. So what we're really talking is a 4-dimensional TQFT. But it's basically spits out vertex operator algebra as an output. So this is a funny version of TQFT, which is vertex operator algebra value TQFT. That's the goal.
Excuse me. Somehow this homology of this modular space seems to depend very drastically on the metrics.
Exactly. So this is, as Kenji pointed out correctly, this is definitely not the space we want to work with. So there are several corrections which I mentioned in passing, and I'll refine as we go. First, both this and this need to be modified. So, and actually there is one more piece of data that needs to be modified, for which we already ready. So we talked about 3 manifolds bounding 4 manifolds. This, in fact, was true in this construction of surgeries of plumbings that we discussed a moment ago. So if your 4 manifold has a boundary, that's also allowed, and in fact it will be necessary if you're trying to glue 4 manifolds from pieces along various boundaries. We have to specify what do I mean by this moduli space, because I have to fix some data along the 3 manifold. Okay. So, right. The modifications to this that you need to make almost from the start the following. First of all, a better behaved TQFT is not the one which arises from Donaldson-Witten theory, where it would be really cohomology of this instanton moduli spaces, but so-called Waffe-Witten TQFT. Okay? So these moduli spaces are much better behaved, and this has to do with the fact that the corresponding TQFT is so-called balanced. I'm not going to elaborate on it much more, but this cures some of the problems. So then I can ask the second question. What about the boundary? What does this particular moduli spaces or TQFT tell me to fix at the boundary? And they tell me to fix flat connection on a 3 manifold, but flat connection for the complex version of gauge group G. So in fact, our boundary data here at the M3 is going to be labeled by homomorphisms from pi1 of M3 into complex version of the group G. That's also quite standard fact in Waffe-Witten theory, and in fact in many of its closed concepts. So therefore, when I'm writing that VOA acts on some huge infinite vector space, potentially infinite, I should also point out that in this moduli space, we fix rho, and as a result, this V carries the label rho. So in other words,
Alphabet means that is in the SDRT paper?
yes.
That's different topography.
Exactly. So it was introduced essentially in that S duality paper that Kenji mentioned, and quite recently, in fact, computations of Pfaff-Witten partition function, numerical invariant, which I'll mention in a second, were subject of quite active study by Goethe, Richard Thomas, and various other people. So this is actually quite active area where, as we speak, there are interesting developments happening, allowing us to compute or understand this theory better on larger and larger classes of four manifolds, which definitely includes scalar ones and so on.
So I think originally it works only for some hyperclear.
Exactly, yeah. So in the original paper, there are very few calculations. And
nowadays it works for more general format.
Yeah, there is Magawa,
Yeah.
Thomas and Magawa.
exactly, yes. Yeah, we won't need all of the computation. So in some sense, what the goal of this work with Bori is to do something complementary where topological invariance has to be built in. So we have to ensure that we're producing a TQFT, but we'll focus, so that's in fact a good point or a good question, we focus on the algebra. So we won't be asking directly about this moduli spaces, so we can use the data of Thomas, Gotchi, and others for checks of what's going to happen here. But we won't be focused on modules. So this right-hand side here is about module of VOA, and we'll be interested in VOA itself in this algebra. So at least this is first kind of approximation to explaining what this VOA aims to do, and if you wish, this is mathematical introduction or formulation of what the goal is. So physically, it's actually going to be extremely similar to what we did with three manifolds. So remember that given a three manifold M3, we wanted to construct some three-dimensional theory T of M3. And again, if you wish, you can label it by choice of root system, which often is suppressed from the notations for brevity, or it's fixed throughout, so therefore I'll do the same. And from that, in turn, we can apply further functors and construct specific partition functions and invariants in many different ways in a rather systematic way. So now I basically want to replace M3 by M4 and T of M3 by T of M4. Okay. So, question to you, and it depends on how well you listen. Can you tell me a priori, without even knowing what's going to happen next, what kind of theory is T of M4? For example, what is the dimension of theory? Previously it was 3D correspondence because we had a three manifold and three-dimensional theory T of M3. So what kind of dimensional theory is T of M4? Yeah, thank you. Well, you're listening. I'm surprised. So indeed, if this is a four manifold, by trying to apply the same rules of the game, we get here two-dimensional theory, and this is, I'm going to ask you, this is version of supersymmetry that it will actually preserve on a generic smooth four manifold, and we're interested in generic smooth ones. I'm not going to settle if this works only for Keller ones or CQ2. I mean, this is not good enough. So in general, it will preserve this much supersymmetry, but it's a two-dimensional superconformal. I'm going to use all the jargon actually. Superconformal theory. Now, just like before, it's supposed to be some esoteric invariant of smooth four manifolds valued in two-dimensional 0-2 theories. Sounds scary. Just as scary as 3D correspondence, which Maxime wanted me to talk about. But here, there is something good about it. Because, first of all, as many of you, of course, used in this calculation, the reason it's a two-dimensional is because 6 is 4 plus 2. So we're using the same six-dimensional five-brane theory as a starting point. And physically, this T of M4 is defined as a compactification of this six-dimensional theory on a four manifold. But now, as we increased 3 to 4, this decreased from 3 to 2, and we're in a good shape. Because mathematically, there is a definition, luckily, of two-dimensional theories. So now we're going to be on a better footing. In fact, even this nonsense about supersymmetry will quickly cancel out because of the following. One of the facts, in fact, the most exciting fact about this supersymmetric 0-2 theories is such that they have left-moving sector and right-moving sector. So this is some terminology from conformal field theory, CFT. This is conformal field theory, not class field theory. Now there are two sectors, left and right. And this is standard terminology from vertex operator algebra, so I'm already entering some. Left sector is supposed to encode holomorphic dependence in variable z, which may parameterize coordinate on some Riemann surface sigma. Likewise, right sector is about dependence on anti-holomorphic dependence, or dependence on z bar. So what this funny notation 0, 2 means is that theory is non-supersymmetric, something that if you don't know supersymmetry, luckily you don't have to know because the left sector is non-supersymmetric. But the right sector is supersymmetric, so it has some supercharge Q, usually denoted by, whatever it is, such that it scores to 0. Okay? And the best thing, once you have some operator in math or physics that scores to 0, is to take its Q cohomology. And once you do that, what happens is basically Q cohomology of any two-dimensional 0-2 theory is one of the most interesting gadgets. And statement is that it's basically usual vertex operator algebra. Why? Because in the right-hand side, on the right sector, it projects you to ground states, something finite, which is usually a finite set or maybe just a single state. And on the left sector, it contains anything because this is operation that only has to do with the right sector. And as a result of applying Q cohomology, you basically get, as a consequence, what may be called holomorphic or chiral conformal field theory. And this is mathematically what a vertex operator algebra is. So vertex operator algebra is basically a statement. It's identical, so maybe I shouldn't say equal, it's really identical to algebra where product may depend holomorphically on Z. Right. Okay. So therefore, if there are any physical ways of constructing this full theory T of M4, you may ask, do I lose any information? Hopefully not. About four manifold and smooth structures if I pass to vertex operator algebra. And now at least this becomes mathematically well defined. And the benefit or the reason it works is because now in low enough dimension that we're talking about field theories whose mathematical definition is inside. Okay, any questions so far? Sorry.
You said the 2 corresponds to one supercharge. That is 4. Would there be 2 supercharges?
Well, there is this Q, and there is also its conjugate Q bar.
I see.
Yeah. So if there are a total of 4, then it would be total 4, which means 2 and their conjugates. Yeah, that's the terminology. But luckily, as you can see, we now bypassed it. Okay, there is one more ingredient I have to tell you, and this is now, so now I can luckily enter just rigorous mathematics. So I'll be talking either about four manifolds, and this is well-defined and rigorous, or I can talk about vertex operator algebras, which is also a branch of math, and I'm just trying to bridge them. That's the whole point. So in some sense, I'm done. The thing is over. This is the basic punchline, and now we can extend or elaborate it in many different directions, and I'll try to do this in the time allotted. So first I want to, so the rest of the talk is basically a list of properties or structures that this vertex operator algebra carries, and we can ask the following questions. How to construct it? Very much like given, say, Kirby diagram or plumbing graph, what are the basic ingredients that we put together? Second question we can ask, how do we show topological invariance? Namely, what are the analogous Kirby moves? Third question we can ask, what are the analogous functors which take us from T of M4 further to more traditional or less traditional invariance, just like we did with three manifolds? For example, can you get Donaldson or Seiberg-Witten out of this T of M4 or vertex operator algebra? So the answer turns out to be yes, at least to the last question about Seiberg-Witten invariance. So that's already good news. It means that this VOA of M4 knows about Seiberg-Witten invariance. It's also more promising in the sense that for constructing new invariants, because it does not necessarily vanish or collapse if you take tensor connected sums of four manifolds. So that theorem I just erased is no longer true in this context. If you take connected sums over three sphere, what happens is that you just do a tensor product of VOA. So for example, analogous statement about this VOA valued invariant is that VOA of M4 connect sum with M4 prime is simply the tensor product of VOA of M4 tensored with VOA M4 prime. And the reason Donaldson or Seiberg-Witten invariance vanished in analogous situation is that moduli spaces actually and their homology of connected sum behave pretty much like this. But then there is this reducibility which at the level of taking numerical invariance produce zero in the end. And that's precisely the benefit why of working with this algebraic structure, that it does not necessarily vanish. Okay. To connect it to Vafa-Witten partition function that I mentioned before, so one thing, once you have vertex operator algebra, you can consider its various modules, and this VRO is one of them or collection of them associated to four manifold. So you can ask about character, chiral, and that's going to be a function of Q, very much like what we saw in the very end of the second lecture. It will be a Q-series development, and it's defined as a trace, or if your algebra contains so-called fermion and Grassmann states, it will be super trace over this module V rho of Q to the L naught. L naught is a special element in the vertex operator algebra, which is usually called stress energy tensor, or rather its specific Fourier mode. So this is, at least according to that general formula, supposed to be under good conditions, where we probably have to ensure that B2 plus is different than 1, and so on, simply Vafa-Witten partition function on M4, Q, and rho, with the same data as before. Therefore, one simple but not very productive way to try to reconstruct vertex operator algebra is to try to compute this Vafa-Witten partition function. It's hard. And then ask, can I recognize this as a character of some algebra? That's basically one way you can try to reconstruct the structure. Luckily for us, Hirako Nakajima did answer precisely this question in his brilliant work more than 20 years ago. So in fact, he did study the homology of these moduli spaces, but on a rather specific set of four manifolds which are LE spaces. I'll call them LE P minus 1. Or rather, maybe A P minus 1. So these are LE spaces. As Kirby calculus practitioner would describe them, they are simply linear graphs of the type that we studied. All of these vertices are colored by or marked with integer -2. So they have a total of P minus 1, 2 cycles, whose normal bundle had order number -2 for all of the 2 cycles, and they have this intersection matrix between adjacent ones according to the linking diagram of A P minus 1. And what Hirako Nakajima computed is basically he studied precisely Waffe-Witten partition function, even though that preceded work of Waffe-Witten, so he had his own definition. And I should say that in current work of Richard Thomas, Gutsch, others, people usually use definition of this partition function in terms of algebraic geometry and counting sheaves rather than gauge theory analysis, but these were expected to be, if not equivalent, but closely related. And what he found, so he computed basically chi rho of AP minus 1, is that this is a character, indeed, of affine Kac-Moody algebra SUP at level n, in case if you're working with rank n or un gauge theory. So from this perspective,
By the way, so before you get for manifold with boundary representation.
yes.
So how is here?
Same thing. So you're absolutely right to point this out. Indeed, this manifold should be viewed as a manifold with boundary. So let me draw the manifold and the boundary. So all of this Fleming diagram encodes a non-trivial skeleton of the manifold in terms of 2 cycles and how they intersect. So this is a cartoon for the actual manifold, and this is its boundary. So this is a manifold with boundary. In fact, that's the same length space boundary we saw before. And if we're careful, we actually notice that this is minus, in my notations, this is minus LP1 as a boundary. But it is a boundary, so I have to fix rho on the boundary. And now, if we recall what rho is a homomorphism from pi1 of the boundary, which we called M3, but I'm slowly switching to entirely 4 manifold notations into complexified group. And then, if you work this out, you'll quickly modular conjugation, of course, as is typical in any kind of gauge theory TQFT, you'll find that rhos are Young tableaus of size P and. So Young tableaus that fit into this box. Okay. If I'm not mistaken.
It's a cyclic group.
Huh?
So the fundamental group is a cyclic group, so how did you get in?
So what is the fundamental group and what does that mean?
Well,
It's a cyclic group.
right, so this is cyclic group ZP,
Okay.
and now I'm mapping it into, I'm looking into representations into complexified UN, but complexification doesn't do much here, so just mapping into UN. So basically I'm looking at a bunch of Pth root of unity modular permutation. And these are Young tableaus, that's very symmetric stuff. And these are indeed the same in one-to-one correspondence with characters of affine Kac-Moody algebra SUP at level n, which are also labeled by the same bit. So in fact, since we spent some time on this point, let me do one cute exercise. I'm going to show you how to obtain at least one non-trivial result already from here, and in my opinion it should have been obtained years ago, and for some reason it hasn't, but it's rather simple. So first of all, let's consider what we just talked about, namely this manifold. So this piece will be a p minus 1, and it has a boundary which is length space of the type p1 up to orientation. And now I want to consider operation. So this is going into a little bit into how we construct more manifolds out of cutting and gluing procedures. I want to consider what it means to add to it an extra node. So basically build out of this as a recursive procedure a manifold AP, just AP, by adding an extra two-cycle. Okay. So this is our space boundary, and so on. So according to Nakajima, we already know what vertex operator algebra should be associated to this piece and the big thing, the whole thing, right? So one of them is SU p plus 1, because we increase p by 1 at level n, and the other is SUP at level n. And according to the axioms of TQFT, if this is really behaves as TQFT, gluing should be such that when we glue something, we basically sum over whatever states we have on the boundary, and once we know the whole thing and a smaller subset, we can extract what VOA should be associated to this particular piece. So if this is our question mark, now it has two boundaries because it has two length space boundaries. One is length space LP1, the other is length space LP plus 1, 1. We can find what this cobordism between length spaces that corresponds to attaching a handle is in the language of vertex operator algebra. And in fact, this is nothing but the coset SU p plus 1 over SUP at level n. Okay. At the level of, so that's easy. But see, without much work, I managed to extract one ingredient, and now I can happily erase this part of the construction because I know what this piece is. And now where I can start building, I can play easily this game by building more and more pieces together. Okay? So in particular now, once I extracted this piece, I can try to construct in analogous fashion more interesting plumbing graphs and so on and so forth. This is about constructing VOA associated to a form manifold. Now let me say a few words because time is short, and probably this is the last thing I can say before chair kicks me out. So about equivalences. Very much like in our discussion of three manifolds, if your construction, sure, it can lead to constructing VOA associated to four manifold, but you want it to be such that if two four manifolds are related by, say, Kirby moves or define the same smooth structure, you want to ensure that the corresponding VOAs also reflect that symmetry, that they're also equivalent in some sense. And there are some simple equivalences which simply follow from the structure of the lattice H2, which already appeared and played prominent role in some of our discussion. And in fact, you can think, roughly speaking, of this VOA as VOA being a lattice algebra for H2 of the four manifold. This is not quite true. This is literally true in a abelian case, but as we already see in the simple example, it's not true if you're studying n greater than 1. But it's a good picture to keep in mind if you want to have intuitive picture of what this vertex separator algebra is. And then it should have some equivalences like this, so that's a simple example. For instance, manifold constructed as a graph, minus p minus 1 here, and its disconnected version minus p minus 1 minus 1 here are the same. So therefore you would expect, or what should happen, is that VOA for these guys is the same. And this basically following M4 constructed by the same data. Now as a smooth manifold. So you can try to go through construction of VOA where it has been done and verify this property. It's actually somewhat simple. It follows from operations on quadratic forms. This is basically a basis change. But I want to describe one non-trivial equivalence of vertex separator algebras that buys something for people who study vertex algebras. And this is new equivalence which has not been seen before. And it represents a Kirby move, which is perhaps arguably the most interesting one. It's called the two-handle slide. And it gives you the following interesting operation at the level of vertex separator algebras, which I'm going to construct as follows. It is, let's look at Grossmanian of k-planes inside n-dimensional space as auxiliary object. I'm going to construct VOA using some algebraic geometry data. Well, it is fairly well known that this is same as Grossmanian of n minus k-planes in n-dimensional space, simply because it doesn't matter if you want to look at plane or its orthogonal complement. And in this context, let me introduce something that may be a little bit less known, but is interesting. First, by defining a fairly standard short exact sequence of various bundles on Grossmanian. So S is going to be universal bundle. Defined as bundle of those k-planes through ON into something which is usually called the quotient bundle. Or also sometimes called orthogonal bundle. So once I have these two basic ingredients, the universal bundle and the quotient bundle on the Grossmanian, I can play the following game. So first of all, S over Grossmanian of k-planes in n-dimensional space is pretty much the same thing as the dual of quotient bundle over Grassmannian of n minus k planes in n-dimensional space. That simply follows, that's analogous statement for bundles of equivalence of those Grassmannians. And here quotient over Grassmannian km likewise is similar to S star over Grassmannian n minus k, comma n. Okay. So these equivalences are rather simple and don't constitute interesting very interesting information. But now we can define the following gadget. I'll define my vertex operator algebra, VOA. So this will be the last step, and I'll stop here. Associated to one of the basic building blocks in this vertex operator algebra. It will be labeled by 3 integers, n1, n2, and n3. 3 non-negative integers. As chiral de Rham algebra, of differential operators constructed by Shachtman, Weintraub, and others, Malikov, Shachtman, Weintraub. And this algebras, what's good about chiral de Rham, these are vertex operator algebras nicely associated to geometric spaces. And as a geometric space, I'm going to take some bundle over my Grassmannian. Okay? In particular, I'll consider the tautological bundle to O plus N3 plus quotient bundle or orthogonal bundle to O plus N2, all sitting over Grassmannian of here N1 plus N2 minus N3 over 2, comma N1. Okay? So here we go. It's a total space of this big bundle that constructed out of basic elements using numbers N1, N2, and N3. So a priori, it's not very symmetric. But the statement about vertex operator algebras that encodes this interesting maneuver called two-handle slide, which doesn't change the four manifold, is basically the statement that as VOA, you have a triality symmetry where T of N1, N2, N3 is the same as this curly T N3, N1, N2, and that's the same as curly T of N2, N3, N1. So even though this is completely non-obvious from the construction, for example, N1 appears here, we're looking at some planes and N1 dimensional space, N3 comes in with a minus sign, so there is no apparent symmetry, and it doesn't simply follow from simple things like Grassmannian of K planes is same as Grassmannian of N minus K planes. Nevertheless, one can check that, and it's highly non-trivial exercise, at least order by order in this chiral de Rham, that this is actually true. And as far as I know, this is one of the new implications of this program for vertex operator algebra. So this is
What's the character of this?
Huh?
What's the character of this?
Okay, it's you can construct it out of a fine Kac-Moody characters, but it's not easy to write. So here I just erased a simpler version of adding a two-handle operation, which was a so-called branching function. So the character of this coset is a branching function. And here you have roughly triple version of this branching function with respect to 3 Kac-Moody algebras. So it's hiding 3 symmetries, namely S. So it has affine SU N1 cross SU N2 cross SU N3 at various levels, which I'm not gonna specify. That will take a little bit more time. I have explicit formulae here. But it's basically character of this gadget is trying to be what branching function is for cobordism with 2 ends. So this is analogous thing which has 3 ends.
Is it isomorphic to this Guyot-Darab-Chak?
As far as I know, no, but I don't know. That's a good question. I guess that's more question to that. Okay, I think I ran out of time. And
what is the argument for why does Muhammad all this stuff as anything?
Okay, so that's a very good question. I'll try to give an answer. I'm not sure if it will be easy or satisfying with something, but intuitively it will hopefully give some answer. So the logic here is that you start with a 4 manifold, then there is some black box. I'll literally draw the black box or the blue box. That involves some physics of constructing this T of M4, so this is mysterious. But then you take Gukov homology and pass to VOA of M4, which is what we're seeing. So one simple answer is that you just compute. You just compute what corresponds to, in this 2-dimensional theory, to operations of adding handles and correspondingly changing handles according to the handle slide operation. That's a very bad answer because I'm using language that's not terribly helpful. What's more helpful perhaps is to say that the reason Grossmanians come about at the technical level, and this may be more useful, is because if you think about this, something having to do with gauge group G and analogous constructions we saw in the case of 3 manifolds, we usually have essentially vector spaces divided by groups. That's what the basic building blocks of T of M3, T of M4, in fact any T are all about. All of QFT is about vector spaces divided by groups. And Grossmanian, my good old friend here, is nothing but, what is it? It's a Keller quotient of C to the n times k double slash UK, right?
With a space of rectangular matrices, and that will be like cubic matrix, like 3-dimensional matrices.
Exactly.
Ah, okay. So that's basically the switch of the 3 sides, 3 dimensions in a 3-dimensional matrix.
Actually, that's a good. You mean for this
Yes.
gadget?
Yes.
Okay, that's a good way to think about it. Yeah. So I like it. Yeah. So Nietzsche says that if this is a square and the duality we're discussing is just switching sides, then they should be thought of as a cube and a cyclic symmetry of rotating cube along the diagonal 1, 1, 1. Okay, that's a nice idea. In fact, it might have something useful hiding beneath it. But anyway, the answer to your question, I guess, is that it's always about vector spaces divided by groups in this T of M something. And that's the reason Grossmanian comes about. And this bundles on top, they also come from something that's being divided, but not exactly in a way that's projected out very compact. So that's where a moment map does allow non-compact directions, but we only get some bundle on top of Grossmanian.
How reasonable is to think about this Q as something which produces Kac-Moody type Lie algebra, your matrix? It's not really, of course, Cartan matrix in any way, but somehow it comes from intersection.
Yeah, it's what Jan is saying is actually true. It works surprisingly well. And the reason is this, actually, okay, so I'll make it louder and make a point out of it. So what Jan is pointing out, if I understand correctly, that we had the Q, which was intersection matrix, intersection form on H2, right? And when Q is linking diagram of some real Lie algebra, basically a natural thing to say is that corresponding VOA of this four manifold, which is, you can think of it as VOA of Q, is basically that Lie algebra, I'll call it Q, affine. Okay, that's muy algebra. In fact, this is how vertex operator algebras were developed, largely by Borchardt and others, trying to set root system and ask what happens if I try to do Kac-Moody algebra for thinking diagrams which are not thinking diagrams of any Lie algebras or root systems. This gives you a big class of algebras called lattice algebras, lattice VOAs. And this indeed plays a rather strong role here, but I have to say it doesn't cover. It covers some of these manifolds we're discussing, and it's useful language to think of gluing and cutting operations because they're beautiful relations, including characters and so on, of those lattice VOAs. But I want to emphasize that this is not the full story. It's coming really short for one simple reason. Its input is intersection form. And that's a very classical invariant of a four manifold. You don't need any fancy stuff to capture this, and this does not capture smooth structures. So this is cool, and it's good to think about what's going on with these VOAs, but this is not cool enough. Because I can easily present to you, even in terms of Kirby calculus, two manifolds which have the same Q, but different smooth structure. Very easily. And vertex operator algebras are different, at least in the examples that one can check. So therefore, while this is a good language of lattice VOAs, it's definitely not the real story.
Any more questions? You see some relation to Simon witness theory. You will simply say that we have some VOA related to this H2. Is there any mathematically defined procedure to recover cyclic invariant from this?
Yes. Okay, so I'll try to say this in words. So Seiberg-Witten equations are this FA plus, or this is for curvature of a connection on line bundle over four manifold, just U1, equals psi bar psi, Dirac operator acting on psi. And psi is a section of a spinor bundle. That's where the choice of spin C structure enters, and so on and so forth. So we look at these kind of equations and try to construct corresponding moduli spaces and Seiberg-Witten, and take integrals over these moduli spaces of first Chern class of universal line bundle to half degree of the space. This is what's known as Seiberg-Witten invariance in some class lambda, where lambda is element of H2 or spin C structure. Now, one quick way to see vertex operator algebra here, even if you don't care about vertex operator algebra, you can see that you're forced. I mean, it's forced upon you. So do the following problem. Study analogous problem where you have several types of spinors. So I runs from 1 up to what physicists like to call NF, so I'll follow those notations, that's fine. So the only thing now is that this moduli space is going to be non-compact. But the natural thing to do, so this also carries index I, is to consider equivariant SUNF version of Seiberg-Witten invariance. And this is going to be well-defined mathematical problem because you can easily show that fixed point sets of SU and F acting on this moduli space are all compact. You can actually study them. It's a cute problem. Somehow, the problem without equivariant action was approached by Jim Bryan and many others years ago, and that was before equivariant became the buzzword in physics and math. And now that it has, nothing stops us from using equivariant SU and F action here. It will come with the corresponding equivariant parameter Zi, where I runs from 1 up to an F. And you can similarly compute this integral. It's actually easy. And what you'll discover is that it's equal to correlator of some operators for 1 through O and F, inserted in point Z1 and Z and F in vertex operator algebra precisely of that type. Because so this VOA is very much still under construction. There are various elements of which have been described, computed, and so on. But I cannot say how to go from there to cyber-equivalent invariance, in part because I have to really have a definition, mathematically rigorous definition of this VOA, and that's again the goal of this ongoing work with Borja. But I can easily go backward. I can start with cyber-equivalent invariance and simply compute them and show that this is indeed a correlator, and the correlation function is going to be in the same VOA. So this is a cute way to see that if you're gauge theorists and don't care about vertex algebras, they'll be forced on you. I mean, this structure is present.
So maybe we don't have more time, so thank you very much. So we start at this research.